another peer programming session. And today we have Vaishnavi with us. She's a graduate analyst at Barclays. She secured an All India rank 50 in the Hash for 2021, and she's a passionate competitive programmer. Thank you so much, Vaishnavi, for joining us today. Now, I would request you to start this session. Over to you, Vaishnavi.
Hi, thank you for the introduction. Um, okay, so I guess this is a peer programming session, right? So we can keep this session as we can discuss some problems, okay, and we can discuss different approaches to the problem. So today we are going to be taking a look at greedy approach, dynamic programming approach, and divide and conquer strategies. Okay. So let me just start with the simplest divide and conquer strategy problem. I'm pretty sure you've had sessions on divide and conquer, right? So can anybody just either unmute their mic or put it in the chat as to what is divide and conquer? Like what is the strategy? I would like if this session would be interactive so that we can have a discussion instead of me just talking about the problem. Okay. Yeah. So Bipul says that divide problems into sub problems, right? So I think even in daily life, when we have a certain task to do, what we can do is we can divide that task into certain sub problems, solve each problem, and then that is how we can solve the entire problem. Okay. So the most basic divide in yeah, right, then solving each of those problems. So the most basic or the most simplest divide and conquer strategy problem that I can recall is the binary search problem. Have you heard about the binary search or the binary search problem? Okay, please don't call me ma'am. Okay. Right. So what does binary search do? Binary search is basically you have been given a sorted array and you need to find an element in the array, right? So what you do is you can either do a linear search on it, so that will take O of n time, right? You search every element one by one, and finally if you get to the particular element, then that particular element is found. But the worst case is O of n if the element is placed in the last, right? You have to search the entire array. So because you have been given the advantage that the array is sorted, what you can do is you can use binary search. I'm just going to share my screen. Okay, is my screen visible to all?
Yes, it's visible.
Okay. So what we are going to do in binary searches, let's say we have an array. I'm sorry, I don't have the code pen, Jamboard. So let's say we are given one. Right. So what do we do in binary searches? We essentially divide the array into two parts. Okay. And then we see that whether the particular element that we are looking for is greater than this one or lesser than this one. If it is greater than this one, then obviously the element will lie in the right sub array. And if it is lesser than this one, then it will lie in the left sub array. We can keep on dividing the array till we get to the particular element. So let's say I'm looking for 2. So I divide the element again, and I have my mid element is 2. So here I found that particular element. So this is a very basic. I'm not going to go deep into it because I think most of you must have done the binary search. So this is a basic divide and conquer strategy. More problems where you can use these divide and conquer strategies is you can look up merge sort, etc. All these problems use divide and conquer strategy. That is, you divide the problem into different sub problems and then solve each of the sub problems. We'll just quickly try to program this particular program a solution for this particular thing. The reason that I'm not spending time on divide and conquer is because I think greedy and dynamic will take up more time. So here I'm just going to quickly code this particular problem. Okay. So just right. So here we have a binary search, right? So let me just define a function binary search. Okay. It will have some parameters. Um, I'm going to write the parameters as and when I code. Okay. So first of all, we need to check for a base case, which will be so when we are coding, like when we are doing the binary search, what is the base case? So when we keep on dividing and dividing, and when we are getting the mid element, right? We are dividing the array into left and right subarrays. But if any time the right subarray becomes greater, like the right index becomes lesser than the left index, that means that you don't have any more problems to divide into. And if you get the element, then you can say the element is found, else the element is not found. So here I'm just going to write down the pseudocode first. This becomes if element is smaller than mid, then check left sub array, and if element is greater than mid, then check right sub array. Okay. And I think that are all the corner cases for this. So if the right index becomes lesser than the left index, then we can just return, like -1. This -1 will just denote that something is not found. Okay. Then we need to find the mid. So mid will be equal to left plus right minus left by 2. So if you have the entire array, you have a left index and you have a right index, right? So what will be the middle? The middle will be the left index plus whatever is remaining, that is right minus left by 2. And I think we need to do a integer division here. So that will be -2. Now, if element is present in the middle, that will become if r of mid. Um, and this is the element that we are looking for. So lm, and I think we can just return the middle, that is the middle index, that is element found over here. Uh, Sorry, I think one second. We need to calculate the middle. So if element is found in the middle, then we can just say element found in the middle. Else, what we can do is, this is an if, right? So elif r of mid. So element is smaller than mid. That is, middle element is greater than lm. We can just do a recursive binary search saying return binary search. And what do we need to pass it? So we will need to pass it that particular array. We will need to pass it the left index and the right index, right? But what will be the left index here while dividing? The left index will be mid plus 1 and the right index will be r. And also I think we need to pass it the element that we are looking for. So here I'm just going to do array left, right, and element that we are looking for. Okay. And if element is greater than mid, then check in the right subarray. So there is no else elif condition more. So I just write an else condition. Return binary search r comma mid. Oh wait, this is the right subarray, right? Sorry, my bad. This is the left subarray. So here it will have left mid -1 Yep, I think this should do it. If element is smaller than mid, so that's R left, mid minus 1, LM. Okay, so I think that is basically our code for binary search. So what we have done here is we have checked if the element is present in the middle, if the element is greater than the lesser than the middle, and if the element is greater than the middle. So let me just check. Just example I want to. We need to look for m equal to. So I'm just going to store the answer. First left is 0. Second left is length of my array minus 1, and then we're going to pass the element. Okay. Now, if my element is not found, then it will return minus 1 for me. So if answer is equal to minus 1, say here, as you can see, it is giving me element found at index 2, so 0, 1, 2. So here I just can say, because array starts from the 0th index, so I just made it 1 element found at index 3, and let me just try something like 7, which is not present, element not found. This is a basic binary search problem, which you kind of keep dividing the problem into sub problems, and you finally solve just one particular sub problem. Okay. The next we are going to be looking at is a very common problem, and that is the Fibonacci series. So does anybody know what a Fibonacci series is? Or how does it work? Like, what is the series exactly? Yes, correct. 0, 1, 1, 2, 3, 5. But how do you generate that series? A of n is equal to A of n minus 1 plus A of n minus 2. This is completely correct. So we start with two numbers, like let's say 0, 1, and then we keep adding those, previous two values to get the next value. And we keep on doing that, right? So here, if you see the pattern, we are doing something repeatedly. That is, we are sort of keep adding two numbers, like we are repeatedly adding two numbers. So we can use a technique known as recursion to solve this problem, right? So let me just share my screen again. So how can we solve the Fibonacci series? So I think we can do a very simple recursion problem. That is, I'm going to just define a function Fibonacci, and we are going to be passing it an element n. Okay. So if n is equal to 0, that is the zeroth element, so we'll just return 0. If n equal to 1, then we just have to return 1, because for the first two numbers we have to consider them 0 and 1, right? And then what we can do, if n is not 0 or n if n is not 1, then we can just recursively call this function Fibonacci of n, say return Fibonacci of n minus 1 plus correct. And this is a very simple recursion program, where what I'm doing is I'm just returning the it will calculate Fibonacci of n minus 1, it will calculate Fibonacci of n minus 2, and it will return me that. So let me just say mm, let's say 5 elements. Is it 5? So yeah, so that will give me 5, right? So it's 0, 1, 1, 2, 3, 5. That gives me 55. You can calculate this if it is giving correct or not. Um, so what are we doing over here? Let me just read this. So we are saying that we have a Fibonacci sequence. So we are doing fib. Let's say we want to calculate fib of 10, right? So we are calculating fib of 10, and we are sending it for recursion. We are doing recursion, and we are saying fib of 10 is actually equal to fib of 9 plus fib of 8, right? And even fib of 9, we are recursively calling this, and we are asking, this is actually fib of 8, fib of 7. It's actually fib of 7 plus fib of 6, and so on, right? So whatever you divide these into 2 again, these into 2, these into 2. So what is happening is we are first calculating Fibonacci of 10 by saying it is fib of 9 plus fib of 8. We are calculating fib of 9 by saying it's fib of 7 plus fib of 8 plus fib of 7, and so on, right? So while doing recursion, what do you think is the time complexity of this problem? So we keep doing this, and we can actually use the recurrence relation to find out the time complexity is exponential, which is 2 raised to n. Okay, so if you keep doing recurrence relation, its recurrence relation will be p of n is equal to if n minus 1 plus p of n minus 2, right? So because we are doing p of n minus 1 plus t of n minus 2, if you calculate all of this and if you bring it down to a series, the final answer will be 2 of n, which is exponential. So is there any way that we can sort of optimize this problem so that it takes lesser time? Can anyone think of an approach where you can optimize this particular problem so that it takes some lesser time to get the same answer? I'll just give you a hint. There is one thing that we are calculating repeatedly. Like here we are calculating fib of 8, and here also we are calculating fib of 8. Here we are calculating fib of 7. Here also we are calculating fib of 7. So is there any way that we don't have to recalculate these values again? Can anyone think of a way? Okay, in general, in programming, if you're calculating something again and again, and if you don't want to calculate it once more, so what do? Loop it. Yeah, but in looping, you're still calculating the value, right? So let's say I'm calculating 2 plus 2, and I'm doing that 100 times in a program. I'm doing 2 plus 2, 2 plus 2, 2 plus 2, 100 times in different places. So if I don't want to calculate these values again and again, is there a simpler way that I can write the program? Forget about Fibonacci, just in general, let's say I'm doing 2 plus 2, 100 times in a program. Is there a way that I can save on that calculation? Recursion, but you're still calculating in recursion, right? Find a mathematical formula is a very good idea. Like you can just use that mathematical formula and not do any operations like recursion. But 2 plus 2 is like a simple formula, right? And I'm doing 2 plus 2 100 times in my, let's say I'm printing, I'm doing 2 plus 2 and then printing it, doing 2 plus 2 and then printing it. So is there a reason that I need to do 2 plus 200 times, or is there something else that I can do? Saving the results. Exactly. So I can just save 2 plus 2 in a variable and then use that variable whenever I want to calculate 2 plus 2. Seems okay? Does this approach seem pretty okay? So can we use the same approach here? Is there any way that we can save these results like fib of 8, fib of 7, so that the next time we want to calculate fib of 8, we don't actually have to calculate it and go into recursion. Instead, we can just save this. I just give you an intuition of what I'm talking about. Let me just delete this. When I say fib of 10, I am actually doing fib of 9. I'm sorry, first fib of 8, right? And then when I'm doing this, I am doing fib of 8 and then fib of 7. Okay. So when I talk about recalculation, when I go into recursion for fib of 10, the compiler will maintain a stack, correct? Because it's recursion, so it will save all that particular state values while I was at fib of 10. Then when I do fib of 9, it will save all that stack values while I'm at fib of 9. Then I go to fib of 8, it will save all the stack values at fib of 8 and it will give the control to the next part of the program, right? When I do fib of 7, it will again save the stack values for fib of 7. Now when I recurse, it will keep popping out these states, and then when I finally reach 10, it will again do fib of 8. So it will again save the stacks, say whatever stack values or stack state, the state variables for fib of 8. Then when I do fib of 7 again, it will again start saving the state for fib of 7, right? So this is what I mean by operation. That is, the compiler will take time to save all these state values and then calculate fib of 7. So I, instead of going into recursion again and doing and saving these state values again, what I can do is I can just save. When I do fib of 8 the first time, I can just save fib of 8 in a variable, and then whenever I need it again, I can just access that variable, so that it doesn't need to go into recursion, save that stack, uh, save that state of the variables, etc. And that is how the time can be saved. So let us start. Let's just try coding that particular thing. Okay, I'm going to just use a dictionary to save all my values. So okay, and now this case, I don't think you have to return anything. Now I'm still doing Fibonacci of n minus 1, and then plus Fibonacci of n minus 2. But here, correct? Is that fine? So what I'm essentially doing is I'll just say Fibonacci of n minus 1 and Fibonacci of n minus 2. When it goes into recursion, I'll just check this dictionary. Is this value already present in the dictionary? Then I'll just return the value and I don't have to do this further recursion. If not, then I'll just do this recursion and save that value in Fibo dp of n. And then finally, I can just print Fibonacci of 10, let's say. Let's do this. So as you can see, it is giving me 55. But right now we are we are saving a lot of space. Sorry, we are saving a lot of time, because we are going to save these values in a dictionary and it doesn't have to recalculate that. So what is going to be, any idea what is going to be the time complexity for this particular thing when we are using DP? Any guesses for what is going to be the time complexity? Okay, let me just open up my window again. Um, so we've done fib of 10, fib of 9, fib of 8. One second, I'll just draw this again. Okay, and this is also going to be so on. So while calculating fib of 10, then we calculate fib of 9, fib of 8, fib of 7, and so on. Here fib of 7 is actually calculated, so we don't have to calculate this. We don't have to calculate this. Here also, while calculating fib of 6, we are going to be calculating fib of 5, so we don't have to calculate this. All of these numbers will actually be pre-calculated. So the time complexity is just going to be the time complexity of calculating this. So fib of 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, which is actually going to be O of n. So the time complexity for this is going to be O of n. As you can see, saving space is actually, we not saving space, sorry, we save time by actually storing the variable, storing the operations results in some variables, so that we don't have to calculate it again. So this time complexity is O of n. Okay, this is known as a bottom up approach. What is a bottom up approach? That means we start from the bottom, that is we start from fib of 10, and then we make our way to finally fib of 1. Okay, can you think of any other approach where we can use dynamic programming, that is we can store some kind of variables and still get to the solution in Fibonacci? Or is there any other method that you can think to solve? Yeah, so that is dynamic programming. So that is what we just did, right? So we did memoization, that is we stored the uh, results in variables and then use that particular, yes. So is there any other, so I showed you two approaches. One is basic recursion and one is DP in recursion using the bottom up approach. Is there any other method that you can think of to solve Fibonacci? Loops. Okay, so you mean like iteration, right? Okay. Can you just tell like how can we solve it using iteration, like a basic, maybe just a basic description of the approach? Yes, so you can take A 0, B is 1, and then for n iterations, you can just do C is equal to A plus B, and then keep reinitializing the variables A and B to the previous values, right? So yes, that is something that you can do, and this actually will take lesser auxiliary space. So for now, our space complexity is O of n, because we are going to be storing all of the operation results in these variables. However, in Sanket's method, that is take A equal to 0, B equal to 1, and then for n iteration C equal to A plus B. So auxiliary space is O of 1. That is, we are not actually storing any operation results anywhere. As we go, we are just calculating the values, and the time complexity for that is O of n, because we are going to be doing it for n times. Okay. Now, i- I hope all of you got the approach that Sanket is talking about. It's a basic iteration approach. Just do so like you have 0, 1, right? So A is equal to 0, B equal to 1. Then you will say C is equal to 0 plus 1. So C will become 0 plus 1, that is 1. Then A will become B, that is A will become 1, and B will become C, that is B will become again 1. So then again you calculate C, that is 1 plus 1, which is 2. And then A and B will become the previous two values. Then again calculate C. So that is the approach that he's talking about. So can you tell me the difference between the two approaches that I mentioned? Sorry, two approaches, that is Sanket's approach and the approach that I told you. One is a very basic difference, that he's talking about an iterative approach, and I told you a recursive approach. Okay, iterative approaches are generally faster than recursive approaches. So I think by all means, Sanket's approach would give us faster, operation wise, it is going to be faster than the recursive approach. And even the auxiliary space that is taken is less. Okay, and he's taking a top up so he's taking a top down approach, that is you start from the top, that is you start from zero, and finally you reach the solution, which is the nth Fibonacci term. Whereas what we did is we started from the nth Fibonacci term, and then we sort of recurse down the recursion tree to fib of 1, right? So the recursive one was a bottom up approach, and Sanket is talking about a top down approach. um, so Sanket's approach in like space wise as well as time complexity wise is definitely better. Is there any sort of pros for the bottom up approach, the one that I mentioned? Can you think of any sort of pros for this particular approach? Clean code. Clean code is a good point. That is because in recursion we generally code it the way we think it. In iteration, finding errors and solving for errors becomes a little difficult because you need to debug the entire program. But in recursion it is very simple because you sort of code how you think about it, right? So there's a base case, and then there's you again solve that particular problem. So looking for errors is like pretty simple while using recursion. Is there any other pros? Are there any other pros that you can think of? It could be faster than Sanket. No, recursions are generally slower than iterations. So no way a recursive solution is going to be faster than an iterative solution. Because so Sanket is also essentially storing the results. I mean, he doesn't need to store the results. Both time complexities is O of n. With map, can you please elaborate? Acha, dictionary, okay. But still, time complexity for both is O of n, as Sanket is doing an iterative solution with n loops, and I'm doing a recursive solution, but I just have to do it to the operation n times. So time complexity wise, Sanket's is better than mine. Okay, so this is something that an interviewer once told me. I also did not know, but it has stuck with me. It is not for this particular Fibonacci series problem, but it's a general approach that they take in the industry. I'm very new to the industry, so I don't know a lot about it. But he told me this. Let me just share my screen. Second. Okay. So when we just mentioned two approaches, bottom approach and a top-down approach. Yeah. So this was when we are doing bottom up is fib of n to fib of 1. And here we'll be starting from fib of 1 and and going to fib of n. Actually, I'll just say fib of n, not fib of n. Here also this is n. Okay, this he said that this is an iterative solution while mine is a recursive one. Time complexity for this, even though both are O of n, recursion takes more time because it's in the hands of the compiler to sort of optimize your problem. So it will take time for the compiler to store the state in the stack, etc. Whereas in iterative solutions, nothing like that is required. So time complexity wise, again, top down approach is going to be lesser. Even space complexity wise, this auxiliary space is O of 1, whereas auxiliary space in our bottom up approach was O of n. The one, again, Kirti mentioned one pro is you can write clean code. Finding errors is easy. Now, the one that the interviewer told me was, let's say I was sending these Fibonacci series over some network. all right? So I'm sending one by one of these terms over a network, okay? So there is a very high chance that, something can go wrong in the network, and those numbers can, introduce some error, or the numbers can be changed a bit. So when I'm sending, like, let's say fib of I reach fib of 10, fib of 9, fib of 8, I calculate fib of 8, but while sending over the network, the answer gets changed to some other number. And same thing here, I'm calculating fib of 1, 2, 3, and while calculating fib of 3, the answer gets changed to some other number. Okay. So what will happen in top down approaches? My whoever I'm sending the number to will calculate fib of 3 as the wrong number. Then I'll send fib of 4. I'll do 3 plus 4, and my final answer is going to be changed exponentially. Okay. And I have no way of knowing if my final answer is right or it's wrong, because there's no way of checking. I'm just calculating the numbers that are being sent to me over the network. If those are changed and some error is introduced, I have no way of knowing if the final answer is right or not wrong. Whereas let's check the bottom up approach. I start with fib of 10 and some error is introduced in, let's say, fib of 8. I keep on calculating, calculating, calculating. I know my final answer, that is fib of 1, is going to be 1. So while sending these numbers over the network, something goes wrong in between. The final answer, that is fib of 1, is not equal to 1. I definitely know that there is some error somewhere. It will not happen if it's just in one machine, but let's say we are working over, different machines. So final answer is fib of 1 is not equal to 1. Then I know some error is introduced, and I can scrap the entire operation and restart the operation. So this is not for Fibonacci series, but in general, bottom up approach helps because you know the final answer and you can validate that final answer. Whereas in top down approach, you generally don't know what the final answer is going to be, and that is why if some error is introduced, then you really can't find out if there's some error or not. So this is something that the interviewers told me, and it has stuck with me. So maybe it might be helpful to you in the future. I hope you understood the point that I was trying to make. Okay. I think we have 10 more minutes. So, as this was a peer programming session, if there's anything that you might want to discuss, then we can discuss on that. There was another problem that I actually wanted to take. That was the knapsack problem. So here we are going to be using something known as a greedy approach, and then we'll briefly discuss about the dynamic programming approach. So, has anybody heard of the knapsack problem? Have you ever encountered the knapsack problem? Have you ever solved a knapsack problem? Okay. Okay. Um, yes, on some contests. Okay. This is a pretty standard problem. I'm just going to give a description about it. So let's say you have gone to some shop to buy some things, all right, and then you have a bag with you, or a knapsack. That is essentially the knapsack. You have different items in the shop. Each item is associated with a weight and with a value as in the price, right? So weights can be anything, and the value associated with that item can be anything. Let's say that you can put those items in your bag, and you can also divide those items, that is cut those items or divide it into fractions and then put it in your bag, such that your bag should become full. Okay. And the capacity of your bag is given. So let's say the capacity of your bag is n, and the items are given as weights of items are given as w1, w2, w3, w4, and the price of the items are given as p1, p2, p3, p4. So can you think of an what will you do in a real life situation as to maximize the profit? That is, you want to buy most weighted items in the least price possible. So can you think of an approach as to what you will do in the real life, if you have actually gone for shopping? I hope you got the problem. If you didn't get the problem, I can repeat again. Yeah, I'll just repeat it one more time. Okay. So let's say you have items whose weight is 1, 2, 3, 4, 5. Okay. These are the weights of different items in the store. And the price associated with these items is 52591. This is cost of items. So item with weight 1 has cost 5, item with weight 2 has cost 2, item with weight 3 has cost 5, item with weight 4 has cost 9, item with weight 5 has cost 1, let's say. So here I'll just write uh, sorry, 1 second. So the zeroth item has weight 1 and cost 5. The first item has weight 2 and cost 2. The second item has weight 3, cost 5. The third item has weight 4, cost 9. And the fourth item has weight 5, cost 1. Okay. And you have a knapsack over here whose knapsack is essentially like a carrying bag or anything that you want to call it, whose capacity is, let's say, 10. So you can only carry weight of 10 in this particular knapsack. Which items are you going to choose to carry in the bag? And you can just cut items and divide them into fractions and put it into your bag. That is allowed. So which items are you going to choose to put in your bag and why? The first one is weight 2 and cost 2. So let me just write that. So you're going to be taking the first one, first item, weight 2, cost 2. Next, sorry, zeroth item, weight 1 and cost 5. Okay, take the zeroth item, weight 1 and cost 5. Okay, next, third item, that is weight 4 and cost is 9. Next, second item, so that is weight is 3 and cost is 5. So our total capacity is 8 right now. And then first item. Okay. And cost is 2. So the total weight comes down to 10. So my knapsack is full. And how much is the cash? How much is the cost? Check out. So that is 5 plus 9 plus 5 plus 2, which is 21. So I'm paying 21 rupees for like worth 10 kg of items, right? Whatever 10 units of items. Is there any other way that I can maybe, in lesser cost, have items that can fill the knapsack with 10 units? Anyone else? Oh, then no, you need to calculate for minimized cost, right? Because when you go for shopping, you want to minimize your cost. Is there anyone else who would like to try? Or is there any general approach that you can, think of going to the shop and buying these items? Is there any general approach that comes to your mind when you want to minimize the cost and maximize the weights? Okay. People says find ratio per unit weight and pick least ratio. Okay, least or most will depend on how, like, what is the ratio that you're taking, weight by cost or cost by weight, correct? Um, okay, so I generally take weight by cost. So for that, I take the maximum like ratio. Okay, so they say that you need to find ratio per unit weight. Is there a reason why you thought of this solution? This will tell the actual cost of each item. Correct. So when we take a ratio, we actually find out what is the value for that item per unit weight. Exactly, people. So we find out. I'm so sorry for the background noise. So we find out what is the value for that item per unit weight, and then we can pick the items with which give us the most value. So for here, I can just take weight by this, right? So it's going to be 1 by 5, 2 by 2, 3 by 5, 4 by 9, and 5 by 1, right? So this is going to give me 1 second. 1 by 5 is going to be zero point 0.2. This is going to be 1. This is going to be 3 by 5 is 0.6. 4 by 9 is 0.444. Okay, and 5 by 1 is 1. So these are the ratios that will tell me what is the value of that item per unit weight, right? So here I just pick out whichever is the maximum, whichever is giving me the maximum value. So for now, 5 is the maximum out of these. So I'll take 5. The next is 0. The next is 1 that is giving me the maximum value. So then I'll take 1. Then I have 0 0.6. Okay. So while doing this, I'll just write down what are the weights that I'm taking. So the weight that I'm taking is 5. Then I took 1. So the weight that I'm taking is 2. It gives me 7. And then I took 0 0.3. The weight that I'm taking is 3. So I think that brings me to 10. So these 3 items are the ones that I'm going to pick. So I'm going to pick the fourth item, the first item and the second item, so that it will give me maximum number of like maximum items in the least cost. So here my cost of items will come down to 1 plus 2. So this will actually come down to 8. So first we saw that we can even take items which cost me 21, but the same amount of items I'm getting in 8 rupees. So what we did is we minimized the cost here by taking the ratios. Now, how did we do it? We took the ratio of weights to per unit items, and Then what we did, we took the maximum, whichever is giving me the maximum value. So here I'm using a greedy approach. What does greedy mean? That I'm going to look for the most optimal solution in this iteration itself. So here I'm looking for the most optimal solution, which is 5. Then I took the most optimal solution, which is 1. And then I took the most optimal solution, which is 0.6. So I calculated all of these, and then I got 8. Okay. Now, let's say you were not allowed to divide the items, right? You were not allowed to divide the items and take into the bag. That is, you will never, you might never reach the capacity 10. You might only reach the capacity 9, because item of weight 1 is not present in the shop. In such a scenario, can you still use this formula? Can you still take ratios and still use this formula? So the one I'm talking about is the 01 knapsack problem. You might want to go and search on it, as we have already crossed our time. We can give 5 minutes for any sort of discussion that you want. And you can go and search about knapsack problem. It uses dynamic programming approach, which we already saw earlier. So that is something that you can take a look at. Is there anything else that you want to discuss? Is there any problem, any particular problem that you might want to discuss or solve? Okay, then I think Vishruti.
I guess there are no such questions as of now. So it was indeed a great session. Thank you so much, Vaishnavi Ji, for the session. It was really helpful. And thank you for investing your time and knowledge. And I believe everyone here had a great time in the session. Thank you so much, Vaishnavi Ji.
Thank you. Thank you, God Chef.
Thank you, Dee.
Uh,
Thank
if
you,
you
Dee.
all if you all have, so because this we were short of time, if you all have any questions that you come across which might require help, even like I keep on trying. I get solutions maybe after 2 to 3 days, but I'll definitely try and help you. Okay, so you can just mail me on this email ID, and then I can try and help you out whenever you want. You can go forth and look for like more dynamic programming approaches and problems, more greedy algorithms. These are very frequently asked in interviews, product based company interviews, as well as these competitions like hash code and code jam, not hash code but like code jam and hacker earth, hacker rank problems. So you can go ahead and explore those, and if you have any problems, then you can just mail me at the mail ID that I've given. Okay, thank you so much.
Thank you.
The session is over from our side. Like if you don't have any doubts, you can leave.